Okay, the next title we will discuss is Brayton cycle, the ideal cycle for gas turbine engines. Brayton cycles, gas turbine engines. Okay, in power plants there are different systems, technologies is used for electricity generation in power plants. Some of them are based on renewable energy sources, such as solar power plants, geothermal power plants. Okay, and some of them are fossil fuel-based power plants. These are traditional, conventional power plants, like steam power plants, like gas turbine engines, like internal combustion engines, and they are all power-producing systems. Today we will discuss Brayton cycle, which is the ideal cycle for gas turbine engines. So gas turbine engines are used to produce power. And here on the left diagram, we will have an open cycle gas turbine engine. Let's go through the operation here. So there is a compressor, combustion chamber, and turbine. On the fresh air, atmospheric air is entering the compressor, okay? And it is compressed to a high pressure by the compressor. As a result, of course, temperature also increases. And this high pressure, high temperature air is burned, and the fuel is burned with high temperature, high pressure air in a combustion chamber. Okay, so this fuel is usually natural gas, but it could be any fuel, of course, but natural gas is the most common one. Gaseous fuels are more convenient in gas turbine engines. So let's assume it's a natural gas. So natural gas is burnt by this air in the combustion chamber. And what is entering the combustion chamber is fuel-air mixture. What is leaving is combustion products, including nitrogen, carbon dioxide, water vapor, oxygen, and other small amounts of other gases. And these combustion gases are at high temperature, okay, and this high temperature also they are at high pressure because air was compressed before, so that in combustion chamber pressure is the same, it doesn't change theoretically, ideally, so that the combustion gases are at very high temperature and high pressure. They enter the turbine and they do work against the turbine blades. They rotate the turbine blades as the combustion gases temperature and pressure is reduced as it flows through the turbine. They leave the turbine, the exhaust gas or combustion gases, at much lower temperature and pressure, here ideally at atmospheric pressure. And of course, there is a net work output. This net work output is equal to work output from the turbine minus work consumed in the compressor. Okay, so this is the operation of an open cycle gas turbine, an actual operation of these systems. On the right-hand side, we have air standard model, which is a closed cycle gas turbine engine, which is called Brayton cycle. Here, combustion chamber is replaced by a heat exchanger, and the amount of combustion here is used as the heat input. So the process here is constant pressure heat addition process. So the actual combustion process is replaced by a constant pressure heat addition process. Here, normal exhaust gases are purged into the atmosphere, and this is an energy loss from the cycle, and we use that here by a heat exchanger. So exhaust gases exhausted to the atmosphere is modeled by a heat exchanger. So the air here goes through the heat exchanger. There's a heat output which is equal to energy value of the exhaust gases, so that it comes back to the initial state at the compressor inlet. So in this cycle, air enters the compressor, compressed to high temperature and pressure. It enters the heat exchanger. There is a heat transfer to the air. Air temperature is increasing. Then high temperature air here goes through the turbine producing work. Then its temperature and pressure decreases to the level of 4. And here air goes through a heat exchanger, but heat is rejected at constant pressure. Then it goes back to the initial state, enters the compressor, completing the cycle. Here in this cycle, process 1-2 is isentropic. We model it as isentropic compression process. 3-4 is isentropic expansion process. Constant pressure heat addition, constant pressure heat rejection processes. This is the operation of the Brayton cycle. Okay, so let's look at TS and PV diagrams for this closed cycle gas turbine engine or the Brayton cycle. So on the TS diagram, process 1-2 is isentropic compression. It is reversible and adiabatic, so entropy is constant. Process 3-4 is isentropic expansion, reversible and adiabatic, entropy is constant. 2-3 heat addition at constant pressure, 4-1 heat rejection at constant pressure. Similarly, on PV diagram, the same processes are shown. You can see the constant pressure heat addition process here, constant pressure heat rejection process here. Okay, now we understand the operation of the cycle. The next thing we will discuss is thermodynamic analysis of this cycle. Thermodynamic analysis. Okay, I would like to stop here before we go through the thermodynamic analysis. Do you have any question? Do you have any questions? Okay, Umut would like to ask a question. Umut Demirdoyer. Are you my student? Are you sure you are my student? Your name is very unfamiliar to me. Are you in the class? Official student in the class? I don't have a student called Umut Demirdoyer. Okay, any questions? Any questions? Are there any questions? Okay, go ahead. You can ask your questions by writing on the chat, or if you have a microphone, you can use your microphone. Any questions? Okay, let's take a break for 5 minutes. This is the end of this class session. After 5 minutes, we will continue. Okay, I am back. I am back. Now we will continue. Let me share my screen again. Let me share my screen again. Okay, are you ready for the next session of the class? Okay, you are ready and you can hear me. That's a good thing. Okay, so let's go through the thermodynamic analysis of this gas turbine engine cycle, Brayton cycle. And as you can see from here, process 1-2 is isentropic compression. Okay, let's write. Okay. So what between process 1 and 2, there is work input, right? Work in, work 1, 2, which is equal to, it is an open system, right? It's an open system. Compressor is a control volume. So there is energy entering by mass. So per unit mass basis, m dot h1 is entering. Anything else? There is power input. Power input is entering, and energy leaving by mass to the compressor, which is m dot h2. And from here, if you solve for work in per unit mass, you divide by mass flow rate, you will get h2 minus H1. That is work in during process 1, 2. And how about work output in the turbine? We use a similar energy balance. Work output in the turbine is equal to H3 minus H4, and W net is equal to W in minus W out. Okay, so these are the relations, work relations for compressor and turbine and the network. How about heat input? Heat input is equal to H3 minus H2. So we can write for heat exchanger, if you write an energy balance, energy entering by mass per unit mass basis H2 plus Q in is equal to energy leaving by mass per unit basis H3, and from here Q in is equal to H3 minus H2. Similarly, Q out is equal to H4 minus H1. So these are the heat input and heat output, Q in, Q out, work in, work out terms, and the network terms for the cycle. Of course, during process 1, 2, we will use isentropic relations of ideal gases. Between process 3, 4, again, isentropic relations of ideal gases. So let me erase this. Now I erase this. Go to the next page. So, in the previous page, Q in is H3 minus H2. Using constant specific heat, it is Cp delta T. Q out, H4 minus H1. Using constant specific heat, it is Cp delta T. And using thermal efficiency of this Brayton cycle is network over Q in. Network is equal to Q in minus Q out. As a result, 1 minus Q out over Q in. This is Q out, this is Q in. With some manipulations, CPs cancel out, of course, and writing this division by using these terms. And how about this relation? This relation is isentropic relation between 1 and 2. Isentropic relation of an ideal gas under constant specific heats. So this is the relation between 1 and 2, pressure and temperature, between 3 and 4. Between 3 and 4. And using these isentropic relations, here we make a new definition, which is the pressure ratio. P2 over P1 is called pressure ratio. Pressure ratio. So P2 over P1 in the compressor is called pressure ratio. And using this pressure ratio, the Brayton cycle thermal efficiency becomes equal to this 1 minus 1 over Rp K minus 1 over K. So if you look at this equation, mathematically, it should be easy for you to see that Brayton cycle thermal efficiency is a function of two parameters, pressure ratio and specific heat ratio. Specific heat ratio for air is not changing much, so the main parameter here is the pressure ratio, and mathematically, it is easy to see that as the pressure ratio increases, thermal efficiency increases. This is given here in this diagram, thermal efficiency as a function of pressure ratio. At low pressure ratios, as the pressure ratio increases, thermal efficiency increases very rapidly. Then after a certain value, the increase is a little bit slow. Okay, this is the change we expect. And the range of pressure ratios in gas turbine engines are usually between 5 and 20. Between 5 and 20. Okay. So the idea is also given in the second diagram. In the right diagram, on the TS diagram, the effect of pressure ratio on the thermal efficiency or the network output is given here. As you can see, the higher the pressure ratio, the higher the efficiency of the engine. Okay. So you can see the effect of pressure ratio on the temperatures in the cycles. Okay, and on the TS diagram, the area under the curve is equal to heat transfer, and the difference between Q in and Q out is equal to net work. From here, you can see how the network changes for different pressure ratio values, and there is an optimum value for which the network area is maximized. Okay. Okay. So what are the applications of gas turbine engines? The most important application is, there are two important applications. One is aircraft propulsion. The other one is electric power generation. Electric power generation. And as we said, the higher the pressure ratio, the higher the thermal efficiency. But increasing the pressure ratio means increasing the final temperature, maximum temperature in the cycle. And the turbine blades cannot withstand some temperatures higher than a critical value. For that reason, pressure ratio is limited by the maximum temperature the turbine pods can withstand. Okay. And in gas turbine engines, air-fuel ratio values are usually very high in order to provide also some cooling to the engine components. Okay, so if you look at here, we said that there is work output from the turbine, there is work input to the compressor, and the net work is equal to work out from the turbine minus work input to the compressor. And the fraction of the compressor work, the percentage of the turbine work which is used for the compressor, is quite high in gas turbine engines. And as a result, we have a definition called back work ratio, which is equal to compressor work divided by turbine work. Okay, compressor work divided by turbine work is called back work ratio. Back work ratio. So let me write that for you. Back work ratio is equal to W compressor divided by W turbine. So this ratio is less than 1, of course, as you can imagine. It is less than 1 compressor work over turbine work. And do we want to maximize this back work ratio or minimize it? Do we want to maximize it or minimize it? The back work ratio. Do we want to maximize it or do we want to minimize it? Back work ratio. Okay, I am not getting any answer. Let me answer it for you. We want to minimize the back work ratio, right? We want to minimize it. Because we want to use less work for the compressor so that net work is maximized. Okay, development of gas turbines. So in the history of development of the gas turbines, what are some measures in order to increase the efficiency and the performance? One is increasing the turbine inlet temperatures. Okay, increasing turbine inlet temperature will improve the turbine efficiency. You can understand that from the Carnot cycle efficiency, right? The higher the TH, the higher the efficiency of heat engine. The same is true for actual heat engines, like gas turbine engines. So you want to maximize turbine inlet or firing temperatures. The other measure is increasing the efficiencies of turbo machinery components, turbines and compressors. Of course, the technology for turbines and compressors are well developed. They are very, very well. And their manufacturers are improving their efficiencies all the time. Now their efficiencies are quite high, actually. And the third method of increasing the performance or efficiency of the gas turbines is adding some modifications to the basic cycle. So what we considered so far is the basic cycle, simple cycle. So some modifications will really help improving the efficiency. Here we see the difference between actual gas turbine cycle and the ideal Brayton cycle operation. And basically the difference is irreversibilities, and irreversibilities are due to friction and unwanted heat transfer. And another source of irreversibility is the pressure drops in various components in the cycle. One of the main modification difference between the actual and ideal cycle is the compression process in the compressor and expansion process in the turbine. In the ideal cycle, we assume it is reversible and adiabatic, so isentropic, but in an actual cycle, it is not really isentropic. So this deviation from the ideal behavior can be accounted for by using isentropic efficiency of the compressor and isentropic efficiency of the turbine. Isentropic efficiency of the compressor is defined as isentropic work over actual work. For the turbine, actual work over isentropic work. And how do you find isentropic work in the compressor? H2S minus H1. What is the meaning of H1? Enthalpy at the inlet of the compressor. What is the meaning of H2S? The enthalpy at the compressor exit if the process was isentropic. For that, S2 is equal to S1. And H2A here represents actual exit state for the compressor. So you have the similar description for the turbine formula.